Okay, so our next lesson is on factoring and solving polynomial equations. So first, let's review some factoring that we had done back when we were doing the chapter on quadratics. So there's basically, you can have quadratic trinomials or you can have quadratic binomials. Of course, you could technically have a quadratic monomial, but you wouldn't need to factor anything with that. So if you have a quadratic trinomial, and there is no coefficient on that x squared, then you're going to want to just simply take that first term and break it up into x and x. And then you want to figure out what two numbers multiply to get that last term, 15, and subtract to get 2. So that would be positive 5 minus 3. And those are your two factors. Now, number 2, you could also factor it the same way, splitting up the x into two x's. Splitting up the 25 into two numbers that multiply to 25 and add up to 10, which would be 5 and 5, of course, both positive. And then, of course, whenever you get the same answer twice, you can write that as the square of a binomial, which would be x plus 5 squared. Now, if you recognize that trinomial as a perfect square trinomial, you could have just skipped that normal factoring with the two parentheses and just gone straight to that square of a binomial. Now, number 4 is a difference of two squares pattern because you have two perfect squares with a subtraction sign in the middle. So this is when you want to split it up equally, right? So 4x squared would be 2x and 2x. So basically, what's the square root of that term? And same thing for the 25. If you square root 25, you get 5 and 5. But the key here is they always need to have opposite signs because when you multiply a positive and negative, you get that negative. Additionally, if you would add up positive 10x and negative 10x, they would cancel out, which is why there's no middle term there. Now, number 4, we only have the two terms, and it's not a difference of two squares pattern because 1, it's an addition sign, and 2, 15 is not a perfect square. However, in this case, you're just going to look for some kind of a GCF. So both of these are divisible by 3, and they both have some version of an x, so the smaller one would just be that single x there. So that's the GCF that you're going to divide out. 9x squared divided by 3x is 3x, and 15x divided by 3x would be 5, and that would be how you factor that one. Okay, so moving on, we're now going to go into factoring the sum and difference of two perfect cubes. So the key is you want to look at your two terms. Now, the good thing with these is it doesn't matter if it's an addition or a subtraction sign in the middle of the two terms because both of them can be factored. But you are going to need to figure out what those roots are. So if you have a numerical value, you're going to figure out what is the root there. If you have a variable, you want to make sure that it's something that's being cubed. Now, just to kind of list our perfect cubes here, if you want to have them as a reference. Okay, so perfect cubes. So if I did 1 cubed, I would get 1. 2 cubed would be 8. 3 cubed is 27. 4 cubed is 64. 5 cubed is 125. 6 cubed, I believe, is 216. 7 cubed, 343. 8 cubed, 512. 9 cubed, I believe, is 729. And then 10 cubed is 1000. So that's just a quick reference. Of course, you could get those on your calculator at any point. Okay, so first thing you need to do when you're factoring the sum or difference of two cubes is make sure that's what you actually have. You have two cubes. So x cubed is pretty easy to tell that we have an x that was cubed. But to get the 8, we want to figure out, well, what number was cubed to get that 8? So what's the cubic root of that number? And it's just 2. So once you know that, now you know that this x here is going to represent your a in this formula or pattern, and the number 2 is going to represent the b. So when you go to fill in the binomial portion of your pattern here, it's basically just going to be adding up those two roots, and whatever sign you have in the original problem, which in this case we have an addition sign, is also going to be in that binomial. The trinomial portion of your factorization here, you're going to take that first term, that x, and square it, so it would be x squared. The next sign here is always going to be the opposite of what the original sign was, or what this was. So that would be a subtraction sign here. Then the middle term, you multiply the a and the b together. You multiply those two roots, so 2 times x would be 2x. And then your last term, which will always be positive, you take your b value, or that second root, and you square it. So 2 squared would be 4. And that would be what our sum of two cubes factorization looks like. So now if we do something like number 2, okay, this one, the x has a number in front, so we have to figure out what the cubic root of that number is, and it's 3. So we have 3x being cubed here, and of course 1 cubed is still 1. So now if I want to factor this one, my initial binomial parenthesis, notice here this is a subtraction or difference of 2 cubes, so that first little binomial is going to have a subtraction sign as well. So I'm just going to carry down my that 3x minus 1 here. And then in my trinomial, I'm going to do 3x squared. Now be careful, because when you do that, remember the 3 and the x are getting squared, so it's actually going to be 9x squared, which is a common mistake. Sometimes people forget to square the number as well as the variable. Then the middle term we know is going to be addition sign, because it has to be the opposite of what the original problem and that first binomial were. And now we're going to multiply together those two roots. So 3x times 1 would simply be 3x. And then our third term in the trinomial is always addition sign there, and you're just going to square that last term. 1 squared is just 1. So that's how you would do a difference or sum of two perfect cubes. So let's just practice a couple more of these. So if we were to do number 3, we know that this here is x cubed, and 64, the cubic root of that is 4, so it's really a 4 being cubed there. And now we just want to use those patterns to fill in this information. So the first binomial here is just going to be those two roots with the addition sign, x plus 4. The second parenthesis, which is our trinomial, will be x squared minus 4 times x, which is 4x, plus 4 squared, which is 16. Okay, number 4, our root here is 5x, and our root over here is 2. So our binomial term will be 5x minus 2, and then the trinomial will be 5x squared, which actually works out to be 25x squared, plus 10x, because you have to multiply those two roots together, plus 2 squared, which is 4. All right, and then we have 2 more of these. Okay, so 216, I believe that root there is 6. This is 6x cubed, and then, of course, 1 cubed. So the binomial factor is 6x plus 1, and then the trinomial factor will be 36x squared, because we have to take that 6x and square it, then minus 6x, because 1 times 6x, when you multiply them together, you just get 6x, and then plus 1, because 1 squared is 1. Okay, so let's do another one here. This one, the root is 10x, and the root for 729, the cubic root there is 9. So we have 10x minus 9, and then in our trinomial, we're going to have 100x squared plus 90x plus 81. Okay. So now the second type of factoring we're going to go over is factoring by grouping. Now, factoring by grouping is very similar to the AC method that we did back in the quadratic chapter. It's sort of like that second portion of AC method. So when we had done AC method, we used the A value and the B value to come up with what numbers we needed to use, and then we rewrote that trinomial into a 4-term polynomial by taking that x value and splitting it up into 2, and then we did our GCF on the first 2, GCF on the second 2, and then kind of wrote our factors. So that process up there is going to be very similar here. The only difference is we have 4 different degrees here when we're going through our terms, but the process will be the same. So first thing we're going to do is make sure it's in standard form. First of all, it has to go in descending order, and you need at least 4 terms, right? So the first one here, you would take out your x squared, and you're left with x minus 2. And in the second pair, your GCF would be a negative 9, and you'd be left with x minus 2. Just like before, when you have those two parentheses, you want to see the same thing inside them. So we have x minus 2 in both of those, which is a really good sign. So now we take those two GCFs, which are the x squared. There we go. Which is the x squared term here, and this negative 9 term. And then we're going to put those together as one of our factors. And then that x minus 2 is our second factor. Now, when we did this previously, the highest degree we had was a 2, so we didn't have to worry about any exponents remaining in our factors. They were both just single x degree or linear, right? But this time we have an x squared minus 9. So whenever you still have some sort of exponent in one of your factors, you need to double check it because sometimes you can actually continue factoring that a little more. So that's considered to be factoring completely. And so the higher degree polynomial, the more opportunity there is that you're going to have to do extra steps of factoring. Now, x squared minus 9 is, hopefully you can recognize that as a difference of two perfect squares. So this would factor into x plus 3 and x minus 3. And then we still have that third factor of x minus 2. There's something worth mentioning here, and as we go through this chapter, you'll notice that whatever the highest degree of your polynomial is, in this case it's a cubic polynomial, we're going to have 3 zeros or 3 solutions, okay? It's just that sometimes some of those will be imaginary, so you won't be able to factor to get them. In this case, all 3 solutions could be found by doing these 3 factors. Now, on the last few problems with those cubic problems, notice we had one single x factor, and then our second factor had that x squared. We could have technically continued to factor those trinomials on the second portion. In this case, none of them would have been factorable, and in order to solve for the solutions when we get there, you'd have to do like quadratic formula or something a little bit more lengthy. So for now, we're just going to worry about the factors, though. Okay, so now on this side here, my GCF of the first two terms is x squared, and I would be left with x minus 4. On the second two terms, my GCF is positive 4, and I'm also left with x minus 4. So far, so good. Combining those two GCFs gives me a factor of x squared plus 4, and then the x minus 4 is my other factor. Now, in this case, I cannot factor it any further because even though 4 is a perfect square, it has a sum or an addition sign there, and that is not factorable according to that difference of two squares pattern. It must be a subtraction sign. So that's where we have to stop. All right, number 3. So continuing, grouping the first two terms, grouping the second two, which is why it's called factoring by grouping. So my first two terms here have a GCF of negative 3x squared, and then I'm left with x minus 2. My second group here, I'm taking out a GCF of 4, and I'm left with x minus 2. My two GCFs come together to make a factor, and then I have my x minus 2. Now, the first factor has an x squared, so I want to double check it, make sure I can't factor it anymore. But 3 is not a perfect square. It's a prime number, so I can't do anything with that. There's no GCF. So I'm basically at a dead end with that. Okay, and then the next one here. So the first two terms are going to be grouped. The second two terms are going to be grouped. So the first two terms, my GCF is x squared. I'm left with 2x minus 5. In my second group, my GCF is positive 9, and I'm left with 2x minus 5. So I have x squared plus 9 and 2x minus 5 as my two factors. X squared plus 9 still is an exponent, so I want to double check and see if there's any more factoring I can do there. X squared and 9 are perfect squares, but there's an addition sign, and there's no such thing as the sum of two perfect squares that's factorable. It's only the difference of two perfect squares, so this is as far as I can go with my factoring. All right, so we're going to do 2 more of these grouping problems. All right, so if we take a look at number 5, grouping the first 2 terms and then the second 2, my GCF on the first 2 terms would be 3x cubed, and that would leave me with an x plus 2. On the second 2 terms, I'm going to take out that negative 24, and that would also leave me with x plus 2. So I have 3x cubed minus 24 and x plus 2. Now, if I look at this first factor, I have an exponent there, so I want to see if there's anything else that I can do. Well, I can't, there's no perfect squares right now. However, there is a GCF of 3. So if I take out a 3, then I'm left with x squared minus 8. Now, this is where it gets a little bit interesting because now that I took out my, whoops, that was actually x cubed, sorry. Now that I took out that 3, I still have something factorable because now it's this difference of 2 perfect cubes, and that brings us back to our very first thing that we did in today's lesson. So if we go back and look at those sum and difference of 2 perfect cubes, look at number 1, this problem right here, x to the third plus 8, and we were able to factor it using that sum of 2 perfect cubes pattern. So that's basically what we're going to have to do with that little section right there. Okay, so this one's a minus instead of a plus. That's the only difference. So my binomial will be x minus 2. And then my trinomial will be x squared plus 2x plus 4. So this entire thing is my factored answer. Now this kind of makes sense because I have 1x here, 1x here, and then an x squared here. So that would be my 4 different solutions if I was going to solve. And this problem did start out as a x to the 4th power or a quartic polynomial. All right, number 6, grouping those first 2 terms, I can take out an x cubed and I'm left with x minus 3. When I group my second 2 terms, I can take out a negative 4x and I'm left with x minus 3. So I have x cubed minus 4x as one factor, x minus 3 as the other. Now, obviously, I do have one factor here that still has an exponent, so I want to check and see if I can do some more factoring with that. I definitely can take out a GCF here, so let's see what that does. Now I'm left with x squared minus 4, which is the difference of 2 perfect squares pattern, so I can actually continue with that and make that x plus 2 and x minus 2. And then I still have the x minus 3 on there and also that GCF I took out. And again, this was an x to the 4th. So I have 1, 2, 3, 4 x's that I could solve for. All right, now the final type of factoring that we're going to review here is when you have them in the quadratic form, but that x value is not a square, but it's some multiple of a 2. So the first 2 examples are kind of basically the difference of 2 squares, but instead of it being an x squared, it's an x to the 4th, but you can still root that because x squared times x squared is x to the 4th. So they're still perfect squares. So generally speaking, you should always check for GCFs first, even if the numbers are perfect squares, because it'll reduce those numbers down to smaller numbers and make the problem a little bit easier to work with. But 81 and 16 do not have any GCFs, so we don't have to worry about that here. So we're going to go right into our difference of 2 perfect squares pattern. So we're basically just square rooting all of these items here. So 81 and x to the 4th, if I square root that, I get 9x squared and 9x squared. If I square root 16, I get 4 and 4. And of course, I need opposite signs because this is difference of 2 perfect squares pattern. Now, both of these still have exponents. I want to check them to see if there's more factoring I can do. The first factor there is the sum of 2 perfect squares, so I cannot do anything further with that. But the second one here is the difference of 2 perfect squares, so I can take it down another level. 3x and 3x plus 2 and minus 2. So your final factored answer would consist of all 3 of these. Since it was a 4th degree polynomial, I have 2 single x's and an x squared, so theoretically I'd have 4 solutions there. Okay, number 2, same concept here. We have perfect squares. There's no GCF to take out or anything, so I'm going to go right into my difference of 2 perfect squares pattern. 5x squared and 5x squared. Square root of 36 is 6 and 6, and of course I need those opposite signs. And this particular problem, even though I have those 2x squareds, there's no more factoring that I can do there. All right, now the next two, same process, but they're not difference of 2 squares patterns, so we're just going to do the traditional type of factoring here. So breaking up that x to the 4th, I'm just going to break it up into x squared and x squared. And then what 2 numbers multiply to 6 and add up to get 7? Positive 6 and positive 1. Now, even though 1 is a perfect square, it's still an addition sign here, so there's nothing else I can do. And same thing with the 6, that's not a perfect square, plus it's an addition sign, so nothing I can do there. Okay, number 4, splitting up that x to the 4th power to x squared and x squared. And then the 2 numbers that multiply to get 24 and subtract to get 10. Be careful you don't think of the ones that add to get 10. The ones that subtract to get 10 are 12 and 2. And now that you have those 2 numbers there, unfortunately, neither one of those is factorable anymore. So you would have to just leave your answer like that. And next one, this is difference of 2 squares pattern again, like numbers 1 and 2. So we have 7x to the 4th and 7x to the 4th, because obviously half of 8 is 4. With the 64, we have 8y squared and 8y squared, and of course, opposite signs. 7 is a prime number, so even if the others are perfect squares, it doesn't matter. I can't do anything with that. Okay, and then the last one, 8x to the 8th, I'm just going to break that up into x to the 4th and x to the 4th. So whatever it is, you just split it in half. So obviously if it was an odd number, you wouldn't be able to do that. Then the numbers that multiply to get 18 and add up to 11 would be 9 and 2. And since it's a negative 11, they're both going to be negative. Now, 2 is not a perfect square, so there's nothing I can do with that factor, but 9 is a perfect square, so I can factor this into x squared plus 3, x squared minus 3. And then my other parenthesis here just stays. And again, notice I have 1, 2, 3, 4, plus 4 is 8, and I had an x to the 8th in the beginning. All right, so hopefully now you see the different ways we can factor these polynomials. So we're now going to use that factorization to help us actually get some solutions. So again, reviewing those 2 patterns or formulas that we looked over in the beginning, the sum or difference of 2 cubes, they're there as a reference, and then factoring by grouping as well. Now, when we solve polynomials using factoring, obviously we're going to factor first, and then we're going to use zero product property to find all the real number solutions. We can also find imaginary solutions too, and I'll talk about that a little bit, but we'll get more into detail with those types of solutions in in a few minutes, okay? All right, so solve each polynomial equation. So this first one here, we have the x plus 2. Remember that root there is going to be 2 cubed. And then the second part is x squared. Then you multiply 2 times x and get 2x, but it has to be the opposite sign. And then the last one, you're going to have a 4 because 2 squared is 4. Now this time you have the equal 0, so you actually want to solve whatever you can. Now remember the instructions just say we have to find real number solutions. So the first one is very simple. When you're doing zero product property, you're just adding your factor up to 0. And then you're going to have x equals negative 2. So that's your real solution there. Well, now you have this trinomial here. It's not factorable because there's no numbers that add up to multiply to get 4 and add up to 2. But how do we know there's not 2 answers? Now you could do quadratic formula or completing the square, some other method to find those answers, but we only need to find them if they're real. So a way to know if they're real or not is we go to our graphing calculator, and we would type in, this particular problem is what? X to the third plus 8, right? So I'm going to type in X to the third power plus 8. Now when I graph that, I see that it's only intersecting the x-axis in one spot, and that's the -2 that we already found. So that tells me that even though I technically will have 2 more solutions, because if this is a cubic polynomial, there has to be 3 solutions, the other 2 are imaginary numbers. So if you needed to find them, you'd have to use some other method to find them other than factoring. But right now, we're just going to do the real numbers. Okay, I'll show you how to do a couple imaginaries with some situations, but this one will require a lot of extra work, so we're not going to do that right now. Okay, next problem. So this one is 3x cubed, that's our root there. And then this is 1 cubed, that's our root there. So 3x minus 1. And then over here, we're going to have 9x squared plus 3x plus 1. Now again, because there's that equals 0, that would indicate we have to actually solve and find those solutions. So we're adding the 1, dividing by 3. So my real solution that I can find there is x equals 1/3. I'm going to put this original in the calculator to see if I even need to bother trying to find any solutions for this trinomial, because it doesn't look like it'll be very fun to factor, and if it's not factorable, I don't want to have to spend time doing something else if they're imaginary. So 27x cubed minus 1. So go to my y equals, clear it out. 27x to the third power minus 1. Take a look at that graph. It's only going through in one location, which tells me there's one real answer, and that's the 1/3 that I already found. And then these two would be 2 imaginary solutions. Just like over here, this would provide us with 2 imaginary solutions, okay? So as you do these, find the real ones, and then if there's 2 imaginary, just write down that there'll be 2 imaginary, okay? If you want to find them, you can. Some of them are easier than others. All right, so now we're going to do some factoring by grouping, and then we're going to find the solutions. Now this time again, it's a cubic polynomial, so there will be 3 solutions or zeros. That doesn't mean they'll all be real, though. Some could be imaginary. Okay, so first thing I'm going to do here is take out my GCF of 4x squared, and I'm left with x minus 2. On this side, I'm taking out the -9, and I'm left with x minus 2. 4x squared minus 9, x minus 2. And then, of course, the 4x minus 9 actually is difference of 2 perfect squares. So we have 2x plus 3 and 2x minus 3. Now, in this case, all 3 of these I can solve. So if I do 2x plus 3 equals 0, and I solve this one, I will end up with x equals -3/2. When you solve the second factor, you're going to end up with x equals +3/2. And of course, this third factor here, you're going to end up with a +2. So all 3 of my solutions were real numbers on this particular problem. All right, so let's take a look at number 4. Grouping my terms together. So I have an x squared, and I'm left with x plus 8. Over here, I have a 6, and I'm left with x plus 8. And then my factors are x squared plus 6 and x plus 8. Now the x plus 8, I can easily solve that one by setting that equal to 0. And I would get x equals -8. Now on this other factor, I can't factor it anymore, right? Because 6 is not a perfect square and there's an addition sign. But what happens if I try to solve it? I get x squared equals -6. And when you square root a negative, you get positive or negative. And in this case, it would be I radical 6. So there's those 2 imaginary solutions. So again, it's a cubic polynomial. I had one real answer, which was the only one you were required to find. And then I also have two imaginary answers as well, giving me that total of 3 solutions. But I didn't have to find that. You could have just said 2 imaginary if you want to, but that one was pretty quick and easy, so I would just go ahead and do it. Otherwise, you kind of have to check it on your calculator to see if they're there or not. Okay, so number 5, again, another grouping problem here. So taking out the x squared, we're left with x minus 5. And then on the second group, taking out a 5, and we're left with x minus 5. So my factors are x squared plus 5 and x minus 5. First one here, this x minus 5 is obviously a real solution of 5. And the other one is probably going to be 2 imaginary, but I'm just going to go ahead and solve it since it's just a simple little binomial here. If I subtract my 5, x squared equals negative 5, and then I would square root each of those, getting plus or minus I radical 5. Okay, so you can see it was a cubic polynomial. I had 1 real answer and 2 imaginary, giving me that total of 3. Okay, number 6, this time, oops, this is not a grouping problem because you only have a trinomial. And you do have an x to the 4th, which means we should have 4 solutions or zeros. So I'm going to go out and start this one with the 2 parentheses, splitting up my x to the 4th evenly into x squared and x squared. The 2 numbers that multiply to 36 and add up to 13 are 9 and 4, and they're both going to have subtraction signs because they have to add up to negative 13. Now, 9 and 4 are both perfect squares, and there's both subtraction signs, so that means I can take this down into x plus 3, x minus 3, x plus 2, x minus 2. And then that means my solutions are going to be negative 3, positive 3, negative 2, and positive 2. So I have 4 real solutions for this problem, and I was an x to the 4th polynomial, so I know there's no imaginaries hiding anywhere. And that's it. All right, so number 7, we have another cubic problem. So first thing I know is my roots here are x and 4. Those were initially the 2 things being cubed. So my first parenthesis is x minus 4. And my second one will be x squared plus 4 times x, which is 4x, plus 4 squared, which is 16. Now I know the x minus 4 is going to be a solution of 4, and that's my 1 real solution that I can find, but I know there's 3 solutions here. So can I finish factoring that trinomial? Are there 2 numbers that multiply to get 16 that add up to get 4? Doesn't look like it. So these remaining 2 answers are either imaginary or they're irrational numbers. The only way for me to know for sure is to check on the graph to see if they're going to go through or not. So if you want to put that in the graph, you'll see that there's only 1 x-intercept, which means that these remaining 2 are 2 imaginary solutions. Okay, number 8. So this is going to be 2x for my cubic root there, and then this 125 will be the cubic root of that is 5. So I have 2x plus 5 as my binomial, and then 4x squared minus 10x plus 25 as my trinomial. Once again, my real number answer is going to be negative 5 over 2 if I solve using zero product property. And this trinomial will give me 2 imaginary solutions. Okay? All right, and because this was a cubic problem, I had 1 real and then 2 imaginary. So, all right. All right, so last few here, we're solving with the grouping. So these first 2, taking out the x squared, I'm left with x minus 2. Second group, I'm taking out the 4, I'm left with x minus 2. X squared plus 4 is one factor, x minus 2 is the other. Now, of course, x minus 2, I can solve and get a real number solution there of positive 2. But since this is not the difference of 2 squares, it's the sum of 2 squares, if I go to solve this one, since it's not factorable, I end up getting two imaginary solutions, which would be positive or negative 2i. All right, and then finally, let's see, number 10. So x squared, and we're left with x minus 5. Taking out the negative 9 over here, x minus 5. X squared minus 9 and x minus 5 are the two factors, but x squared minus 9 can be factored again because it is the difference of two squares pattern. So that's going to give me three real solutions. Negative 3 is one of them, positive 3, and positive 5, which is perfect because this was a cubic polynomial, so I have all three of my solutions. This time they're all real numbers. Last example, I had one real, two imaginary. And then the final two problems here. So these are those trinomials, so we kind of want to treat them as we would just a normal factoring problem back from quadratics. X squared and x squared. The two numbers that multiply to 12 and add up to negative 7 would be negative 4 and negative 3. Of course, that first factor there, x squared minus 4, can be factored out into x minus 2 and x plus 2. So now to solve these, I have x equals negative 2, x equals positive 2 for my two real solutions. And if I solve x squared minus 3, I actually have two more real solutions, believe it or not, but they are irrational. You get positive or negative radical 3. So I have 1, 2, 3, 4 solutions for that x to the fourth polynomial. Okay, and then the last one here, x squared, the two numbers that multiply to get 24 and subtract to get 2, positive 12 minus 2. No, sorry. Positive 6 minus 4. Now the plus 6, nothing I can do with that factor. However, x squared minus 4 is the difference of two perfect squares, so x plus 2, x minus 2. Now I can solve it. These two are going to give me two real solutions, negative 2 and positive 2. And then this little factor here will give me two imaginary solutions. And it will be x equals positive or negative I radical 6. So again, it was a fourth degree polynomial. I have four solutions altogether, the two real and the two imaginary.